Today we're going to carry on with amplifier frequency response, chapter 10 in your textbooks. Let's just read the introductory paragraph. Remember when we discussed the various amplifiers in chapter 6, we made some assumptions. So just let's read this introduction here just to make sure that we understand in your textbooks. I didn't underline this, but it's the introductory paragraph on the main page there. It says here, in the previous chapters on amplifiers, the effects of the input frequency of an amplifier's operation due to capacitive elements in the circuit were neglected in order to focus on other concepts. The coupling and bypass capacitors were considered to be ideal shorts, and the internal transistor capacitances were considered to be ideal opens. This treatment is valid when the frequency is in the amplifier's mid-range. I'm going to show you where is the mid-range as well in this chapter. Now, as you know, capacitive reactances decreases with increasing frequency and vice versa. When the frequency is low enough, the coupling and bypass capacitors can no longer be considered as shorts because their reactants are large enough to have a significant effect. Also, when the frequency is high enough, the internal transistor capacitances can no longer be considered as opens because their reactances become small enough to have a significant effect on the amplifier's operation. Alright, so this is what we're going to discuss in this chapter. Please note, we're not going to do this chapter as an entirety. That's why you have to have your textbooks out and underline, because I'm just going to point out the main points that you need to know, because we haven't got time in this Electronics 2 course to discuss this in full detail. But you have to keep in mind that the amplifier's frequency response are influenced by these factors. Alright, what I've underlined there, this is what everything that I'm going to ask you to underline is what you need to know for this chapter. Just a background knowledge about the frequency response. We're not going to do calculations and stuff like that. So it's just theory. So 10.1, the basic concepts. The basic concepts. You can underline the introductory paragraph. In amplifiers, the coupling and bypass capacitors appear to be shorts to an AC at mid-band frequencies. At low frequencies, the capacitive reactance of these capacitors affect the gain and phase shift of signals, so they must be taken into account. The frequency response of an amplifier is the change in gain or phase shift over a specified range of input signal frequencies. You must have seen up to this stage that amplifiers operate, say, normally an audio amplifier from 20 Hertz to 20,000 Hertz, 20 kilohertz. Alright, so that's the range that it can operate over. Anyway, the effect of the coupling capacitors. The effect of the coupling capacitors. Which are the coupling capacitors? If you can recall from chapter 6. Coupling capacitors on the input and the output. So there we've got C1 on the input, C3 on the output. Coupling capacitors. We haven't discussed the JFET yet, the junction field effect transistor. But we will for weeks to come. There is also the coupling and just the coupling capacitors. Alright, so let's read through quickly or mark in your textbooks about the coupling capacitors. Recall from basic circuit theory that XC is equal to 1 over 2 pi FC. You're familiar with this formula, you've done it in electrical engineering as well, and we have discussed it in chapter 6. This formula shows that the capacitive reactance varies inversely with frequencies. So, at lower frequencies, the reactance is greater and it decreases as the frequency increases. At lower frequencies, for example, audio frequencies below 10 Hz, capacitively coupled amplifiers such as those in figure 10.1 have less voltage gain than they have at higher frequencies. The reason is that at lower frequencies, more signal voltages dropped across C1 and C3 because their reactances are higher. Now, this higher signal voltage drop at lower frequencies reduces the voltage gain. Also, a phase shift is introduced by the coupling capacitors because C1 forms a lead circuit with Rin of the amplifier. You're familiar with these terms. by the coupling capacitors with R in of the amplifier, and C3 forms a lead circuit with RL in parallel with RC or RD for the JFET, of course. Alright, so recall that a lead circuit is an RC circuit in which the output voltage across R leads the input voltage in phase. Also stuff that you've done in electrical engineering. Alright, so that is the bypass capacitors. Let's have a look at the effect of the coupling capacitors. Let's have a look at the effect of the bypass capacitor. Where's the bypass capacitor again? C2, ne? We had to look, remember, to determine the voltage gain if it's bypassed. If it's not bypassed, is swamping used or whatever, ne? If you recall from chapter 6. Anyway, in your textbooks, the bottom of page 493, effect of the bypass capacitors. At lower frequencies, the reactance of the bypass capacitor C2 in figure 10.1 becomes significant, and the emitter or the field effect source terminal, but we will still discuss that, is no longer at AC ground. Remember, we assumed in chapter 6 that that is the fact. The capacitive reactance XC2 in parallel with RE creates an impedance that reduces the gain. Alright, and there's an example as well. Okay, which that is in figure 10.2. Alright, so for example, when the frequency is sufficiently high, XC is 0 ohms and the voltage gain of the common emitter amplifier is maximum. Remember, we said we still have to look at the circuit, but it's RC divided by R accent E. Everything is bypassed. At lower frequency, XC is much larger than 0 ohms and the voltage gain then has to change to RC divided by RE plus ZE. Ne? Alright. Just keep that in mind. Alright, that was at the lower frequencies. Let's have a look at the effect of the internal transistor capacitances. Where are the internal transistors? Formed between base collector and base emitter because of the construction. So you can see in the BJT and the JFET that is the case. So I have internal, this is internal capacitances formed in the transistor. Alright, so in the books again, the effect of internal transistor capacitances at high frequencies. Take note, at high frequencies. Previously it was low frequencies. The coupling and bypass capacitors become effective AC shorts and do not affect an amplifier's response. Internal transistor junction capacitances, however, do come into play, reducing an amplifier's gain and introducing phase shift as the signal frequency increases. Alright, so please underline that. That is important. Okay, now we have been introduced that the coupling and bypass capacitors influenced by at low frequencies. We will have a look at the frequency response curve now. And the internal transistor capacitances at high frequencies. Alright, the next sections we aren't going to have a look at. Miller's theorem we're not going to discuss, so we carry on to the decibel, introduction to the decibel. You are familiar with it. Just underline 10.2, the decibel is a unit of logarithmic gain measurement and is commonly used to express amplifier response, and you just have to use equations 10.3, 10.4. Power gain, you have to calculate as 10 log, in dB of course, 10 log power gain, and to calculate the voltage gain in dB, it's 20 log voltage gain. So just keep that in mind. There's some examples there at the bottom of the page as well. Alright, on the next page, 0 dB reference, please underline. It is often convenient in amplifiers to assign a certain value of gain as the 0 dB reference. This does not mean that the actual voltage gain is 1, which is 0 dB. It means that the reference gain, no matter what the actual value, is used as a reference with which to compare other values of gain and is therefore assigned a 0 dB value. I didn't mark it, but you can mark it, especially here where it talks about the mid-range gain, but let's get there. Many amplifiers exhibit maximum gain over a certain range of frequencies and a reduced gain at frequencies below or above this range, as we will see later in this chapter. The maximum gain occurs for the range of frequencies between the upper and lower critical frequencies, which I will also introduce to you a bit later in the chapter, and is called the mid-range gain, which is assigned a 0 dB value. If you go and look at figure 10.7, just below that paragraph, it shows you there at 0 dB AV mid-range gain. And you can see below that mid-range gain how the frequency is influenced by my coupling and bypass capacitors. So any value of gain below mid-range can be referenced to a 0 dB and expressed as a negative dB value, because the signal gets reduced. No? Alright, for example, if the mid-range voltage gain of a certain amplifier is 100 and the gain at a certain frequency below mid-range is 50, then this reduced voltage gain can be expressed as 20 log 50 divided by 100, which is 20 log 0.5, which is minus 6 dBs, as you can see on the figure 10.7. This indicates that it is 6 dB below the 0 dB reference. Halving the output voltage for a steady input voltage is always 6 dB reduction in the gain. Correspondingly, a doubling of the output voltage is always a 6 dB increase in gain. And as you can see, it is indicated there in figure 10.7. Another term that you have to be familiar with at the bottom of the page, critical frequency. Critical frequency, also known as the cutoff frequency or corner frequency, is a frequency at which the output power drops to 1/2 of its mid-range value. Basically what we've discussed now. Now, this corresponds to a 3 dB reduction in power gain as expressed in dB by the following formula. Power gain in dB, remember, it's 10 log, a certain number, 0.5, so it gives me a value of minus 3 dB. If we go and look at that figure again, just above, that we've just looked at again, and then we can see my mid value range, we will discuss that now, 0.7, but here 0.5 is the mid value of my voltage gain. Anyway, let's have a look at the textbook again. I also want you to mark on page 498, just below table 10.1, where it just shows you some the values of the doubling and halving of the voltage gain. Just below that it says, also at the critical frequencies the output voltage is 70.7% of its mid-range value and is expressed in dB as 20 log 0.707, as we've seen on the previous graph. So critical frequencies, output voltage is 0.707 of the mid-range value. Alright, then we're going to skip again and we go to, now we're just going to look at the low frequency amplifier response. We had an introduction to that. Just going to have a look at a bit more detail. You can mark the introductory paragraph there where it says the voltage gain and phase shift of capacitively coupled amplifiers are affected when the signal frequency is below a critical value. At low frequencies, the reactance of the coupling capacitors becomes significant, resulting in a reduction in voltage gain and an increase in phase shift. Alright, so that's what's discussed here. But there's a lot of detail which we are not going to discuss. Just want to introduce you to the Bode plot. If you haven't done it in some subject, we are not going to cover the Bode plot. We just have to look at the frequency response using the Bode plot. On page 503. The Bode plot, a 10 times change, you can underline this as well. A 10 times change in frequency is called a decade. Please, I've asked this question in the exams, and the students write for me that it is a 10-year period. Of course it is a 10-year period, but not in electronics. It's a 10 times change in frequency when we talk about frequency response of an amplifier. So for the input RC circuit, the attenuation is reduced by 20 dB for each decade that the frequency decreases below the critical frequency. This causes the overall voltage gain to drop 20 dB per decade. Alright, as indicated there in figure 10.12. There you can also see, if we can go to the figure there. There you can also see there is some of the values or the terms mentioned here. That FC is the critical frequency that we've talked about. And you can see from the critical frequency the mid-range starts. But we are only looking now at the lower frequency. Remember, that's the axis of the frequency, so it starts here at 0. So this is the low frequency part, which of course is influenced by the coupling and bypass capacitors, as we have seen. And then 10 times change in frequency called a decade, 20 dB per decade. So you can see here that, but we will discuss that in the next picture as well, that the frequency becomes 20 dB lower for each of these RC circuits. Alright, I also didn't underline this. I see now that I've missed it. Just below figure 10.12. It says there, sometimes the voltage gain roll-off of an amplifier is expressed in dB per octave. Rather than dB per decade. An octave corresponds to a doubling or a halving of the frequency. For example, an increase in frequency from 100 Hz to 200 Hz is an octave. Likewise, a decrease as well. So, a rate of minus 20 dB per decade is approximately equivalent to minus 6 dB per octave. A rate of minus 40 dB is approximately equivalent to minus 12, and so forth. Alright. So I just wanted to show you that, and then we skip the rest of the chapter until it gets to the end of this specific section on page 512, where it shows us the total low frequency response of an amplifier. Total low frequency response of an amplifier. Alright, so it summarizes what I've introduced you to so far. It says, now that we have individually examined the high-pass RC circuits that affect BJT, or a FET amplifies voltage and amplifies voltage gain at low frequencies. Let's look at the combined effect of the three RC circuits in a BJT amplifier. Each circuit has a critical frequency determined by the R and C circuits in the BJT, R and C circuit values, R and C values. The critical frequency of the three RC circuits are not necessarily all equal. Alright, they may differ. If one of the RC circuits has a critical or a break frequency, also called break, higher than the other two, then it is the dominant RC circuit. Please underline. If one of the RC circuits has a critical frequency higher than the other two, then that is the dominant RC circuit. The dominant circuit determines the frequency at which the overall voltage gain of the amplifiers begins to drop at minus 20 dB per decade. The other circuits each cause an additional minus 20 dB per decade roll off below their respective critical break frequencies. Let's have a look at figure 1025 so that we can see what happens here. You can see here, remember in the low frequencies case, here's the critical frequency. One of these, whichever one is the largest, is going to be the dominant critical frequency. Ne? That's when we're talking about the low frequency side. Of course, it's going to be the opposite on the high frequency side. We're talking now low frequency side. So that's going to be the dominant critical frequency, and you can see that it rolls off at minus 20 dB. At the next RC circuit, whether it being the output or input or output coupling capacitors or the bypass capacitor, then it's going to drop another 20. So it's making it minus 40 dB. And then for the last one, in this case, the bypass, minus 60. So as you can see, my amplifier, because of these capacitances, actually, if it was ideal, this frequency should have been amplified right through. But as you can see, because of these capacitances, can't amplify right from the beginning, from 0 hertz. Alright, that's the low frequency. But just have a look again in your textbooks below that figure, just to make sure that you understand here. I've underlined something here. If all RC circuits have the same critical frequency, the response curve has one breakpoint at the value of FCL, lower critical frequency, and the voltage gain rolls off at minus 60 dB per decade below that value as shown in the ideal curve in figure 1026. Actually, the mid-range voltage gain does not extend down to the dominant critical frequency, but is really at minus 9 dB below the mid-range voltage gain at the point. Remember, minus 3 dB for each RC circuit. Right, as we've seen in this curve. But there you can see, if they're all the same, minus 60 dB, and the blue one shows the actual one. Alright, so that is a summary of the total low frequency response of an amplifier. Let's have a look at the high frequency amplifier response on page 517. When we were introduced, what influences the high frequency? Transistors' internal capacitances, ne? Transistors' internal capacitance. So mark the introductory paragraph which says, you have seen how the coupling and bypass capacitors affect the voltage gain of an amplifier at lower frequencies where the reactances of the coupling and bypass capacitors are significant. In the mid-range of the amplifier, the effects of the capacitors are minimal and can be neglected. If the frequency is increased sufficiently, a point is reached where the transistor's internal capacitances begin to have a significant effect on the gain. The basic difference between the BJT and field effect transistors are the specifications of the internal capacitances and input resistances. But we will still discuss the field effect transistor. Alright, that's the introductory paragraph of the high frequency amplifier response. Then we skip the rest of the chapter, because we haven't got time to go into depth. You just have to realize that an amplifier can't amplify the whole range, frequency range. Alright, now we go to the summary for the high frequency response of an amplifier. And mark there as I've done there. Total high frequency response of an amplifier. As you have seen, the two RC circuits created by the internal transistor capacitances influence the high frequency response of both the BJT and the field effect transistor amplifiers. As the frequency increases and reaches the high end of its mid-range values. Where's the high end of the mid-range value? We will have a look now. One of the RC circuits will cause the amplifier's gain to begin dropping off. The frequency at which this occurs is the dominant upper critical frequency. It is the lower of the upper critical high frequencies. Remember, the dominant lower critical frequency was the largest of the three. I'll show to you now when we look at the whole picture. The dominant upper critical frequency is the lower of the two. Keep that in mind. But anyway, if we go and have a look at figure 1044, there I can see my two RC circuits formed by the transistor's internal capacitances. There's my mid-range. Remember, amplifier will amplify that fine. As soon as the frequency becomes too high, then this happens. Minus 20 dB for the one and another minus 20 dB for the other one. Remember, the upper critical frequency determined by the biggest or the largest of the two. Mid-range, minus 3 dB. Okay? And of course, as I said, up to there is the mid-range value. So the amplifier is not influenced. Then we neglect the capacitances because it doesn't have that bigger influence. Alright, to get back to the textbook, now we're going to look at the total picture. The total picture at the bottom of page 527. Total amplifier frequency response. In previous sections, you've learned how each RC circuit in the amplifier affects the frequency response. In this section, we will bring these concepts together and examine the total response of typical amplifiers and the specifications relating to their performance. Very important, this page, what I've underlined there. Alright, figure 1045 shows a generalized ideal response curve Bode plot for the BJT amplifier shown in figure 1045A. As previously discussed, please underline all this. The three breakpoints at the lower critical frequencies FCL1, FCL2 and FCL3 are produced by the three low frequency RC circuits formed by the coupling and bypass capacitors. Low frequency. The breakpoints at the upper critical frequencies FCU1 and FCU2 are produced by the two high frequency RC circuits formed by the transistors, internal capacitances. Now, I've mentioned this now about 3 times, so I'm sure that you get the point by now. Alright, but let's have a look at figure 1045. That circuit should also look familiar. Common emitter amplifier using voltage divider biasing and swamping. So I have coupling and bypass capacitors. And there's the total frequency response of this amplifier. Please, you have to be able to draw this and explain basically what happens. Voltage gain against frequency in dB. Here's my mid-range. Remember to include the labeling as well, otherwise marks can't be awarded. But here you can see the 3 lower critical frequencies, and you can see which one is the dominant. Dominant lower critical frequency is the largest of the 3. And here you can see is the 2 upper critical frequencies formed by the transistors' internal capacitances. Which one is the dominant? Smallest one of the 2. Okay. And remember, from there to there is the mid-range. Okay, from there it starts for each RC circuit minus 20 dB, minus 20 dB, minus 20 dB, and also on the upper side. Alright. Another thing that you should mark, let's go back to the textbooks there quickly. Mark that paragraph below figure 1045 as well. Of particular interest are the 2 dominant critical frequencies. We haven't shown that yet, but please mark that as well. In figure 1045B, these 2 frequencies are where the voltage gain of the amplifier is 3 dB below its mid-range value. These dominant frequencies are designated FCL DOM and FCU DOM, as we have just seen in figure 1045. Alright, the upper and lower dominant critical frequencies are sometimes called the half-power frequencies. This term is derived from the fact that the output power of an amplifier at its critical frequencies is 1/2 of its mid-range power, as previously mentioned. This can be shown as follows, starting with the fact that the output voltage is 0.707 of its mid-range value at the dominant critical frequencies, as you can see in that little formula there. So, P out, critical frequency is V squared out FC divided by R out, and you can see finally, with calculation, 0.5 P out. Alright, half power frequency. So, alright, and then the last thing that you have to know in this chapter is the bandwidth. You have heard of bandwidth before. What is bandwidth? An amplifier normally operates with signal frequencies below critical frequency and the dominant upper critical frequency, as you know. When the input signal frequency is at the dominant lower critical frequency or the dominant upper critical frequency, the output signal voltage level is 70.7%, its mid-range value, or -3 dB. If the signal frequency drops below the dominant lower critical frequency, the gain and thus the output signal level drops at 20 dB per decade until the next critical frequency is reached. The same occurs when the signal frequency goes above the dominant upper critical frequency. Now the range or the band of frequencies lying between the dominant lower critical frequency and the dominant upper critical frequency is defined as the bandwidth. It's defined as the bandwidth. So as we go back to our books, if I ever ask you in the test or the exam to explain this for me, and you have to draw this generalized ideal response curve of the Bode plot, then you have also to show me where is the bandwidth measured. And it's from that to that, which are the dominant lower critical frequency and the dominant upper critical frequency. That is the bandwidth. And if I have these values known, then it of course is the dominant upper critical frequency, and I subtract the dominant lower critical frequency from it. That is as shown in the formula at the bottom of page 528. Equation 1027 to determine the bandwidth. Alright, this concludes this introduction. Basically it's just an introduction to the frequency response. As you can see, there's a lot of calculations or whatever that can be done. But make sure that, I hope you've marked everything. Read through the sections discussed. You should be able to explain the basic concepts with the aid of sketches. And of course you should be able to show how and determine the bandwidth as we've discussed lastly. Alright.